Hello everyone. This video is titled Solving IVPs, right, initial value problems, using Laplace transforms. Now I've done several videos on this before, but in each video a different concept is being used. So in this particular video, the second translation theorem, or translation about the t-axis, is being used. And I've done in a previous video, I've talked about the second translation theorem and the unit step function. Right, so I'm assuming you know what those are before I continue on with this video. So I'm not going to go over the second translation theorem or what the unit step function is. All right, that's all in a previous video. Right, so again, please look over that or read on that stuff before watching this one. All right. So it's the same procedure, really. It's the only thing is here, certain functions in my expression, certain functions in my equation are piecewise defined functions. And again, if you recall from my unit step function and second translation theorem video, you should be able to write piecewise defined functions that are defined for non-negative values of t. You should be able to write those using unit step functions. Alright, so here I have used the Laplace transform to solve the given initial value problem. And I'm just going over two examples. So the differential equation is y prime plus y equals some function of t. The initial condition, y of 0 is 0, and this function of t is a piecewise defined function. Where f of t is 0 from t equals 0 to 1 but not including 1, and f of t is 5 for t greater than or equal to 1. Now you could go about your business by replacing f of t with 0, finding your function y, and then say, hey, y equals this when t is between 0 and 1, and then let f of t be 5, solve that resulting equation, and say, oh, y is that when t is greater than or equal to 1. So you can write your solution as a piecewise defined function as well, just taking one piece at a time. But again, I'm not going to do that here. I want to use our second translation theorem and some unit step functions. Alright, so if you recall from last video, again, I should be able to rewrite this function here, f of t, without the pieces. Right? And if you go along with this would be 0. And then I take away the first piece, minus 0 times the unit step function at t minus 1, right? That gets rid of the first piece after t equals 1. Not really necessary because the function's 0 there, but I'm just doing this for teaching purposes here. Then plus the next piece, again only after t equals 1 though, so 5 times the unit step function at t minus 1. Alright, and that'll add on 5, but only for values 1 or greater. Alright, so all in told here, f of t is simply 5 times the unit step function at t minus 1. Okay, so I'm going to replace f of t with this and not worry about it as, this function here, right, the way it's written with the unit step function is exactly the same meaning, has exactly the same outputs as our piecewise function. Only it can be written in one line, so that's most likely why the unit step function is used. It cuts down on writing. So I replace f of t with that, y prime plus y equals, and then f of t is this 5 times the unit step function at t minus 1. Alright, then I go through and do this the way I would any other initial value problem using Laplace transforms. Right, the first step is I take the Laplace transform of both sides. So we have the Laplace transform of y prime, which I'm going to be assuming that you know from previous videos or previous reading how to take the Laplace transform of derivatives. Then we have plus the Laplace transform of y equals the Laplace transform of 5 times this unit step function at t minus 1. Alright, so this, so I'm going to let, off to the side here, I'm going to let capital Y of S be the Laplace transform of little y of t, or just little y. Now, the Laplace transform of the first derivative, that would be S times y of S minus the value of y at 0, little y at 0. Then we have plus the Laplace transform of y, I called, again, capital Y of S. And over here, now this is where you're using the second translation theorem. Put this in a different color. Again, I'm not going to go into what that all is. I did a whole nother video on this. So let's tell you what this is going to be. All right. So first off, I'm going to pull 5 out of that. And then we have the Laplace transform of the unit step function at t minus 1. All right, and I'll tell you right now, this will be e to the negative 1s over s. All right. Okay, so I'm sorry that my s's look like my 5's. This is a 5 here, times e to the negative s over s. Alright, and then knowing that the initial condition, y of 0 equals 0, this term's gone, alright, that's 0. And then I solve for y of s. So part 2 is solve for y of s. Now, if I factor y of s out of here, I have s plus 1 left over, and I divide by that. So y of s would equal 5 times e to the negative s over s times s plus 1. And now I can solve, take the inverse Laplace transform. And this is again using, go to the next page here, using the second translation theorem. So the third part is, y of t, the solution to our initial value problem, is now I'm going to pull the 5 out. It's 5 times the inverse Laplace transform of e to the negative 1s times 1 over s times s plus 1. All right. So again, using the second translation theorem, the value of this is e to the negative 1s. The value of a is is positive 1. And then this rest of the expression I'll call, this is capital F of s, which is the Laplace transform of some function little f of t. And I'm going to break that up using partial fraction decomposition. So this is equal to some constant over s plus some constant b over s plus 1, multiplying through by the denominators. You have 1 equals a times s plus 1 plus b times s. So we get a equals 1, b equals negative 1 here. I hope you can tell. So we're getting 1 over s minus 1 over s plus 1. So, taking the inverse Laplace transform of this, we have little f of t equals 1 minus e to the negative t. I'm assuming you know your basic inverse Laplace transforms. Alright, but now you apply, once again applying the second translation theorem. We get the following. Y of t would be equal to 5 times, and then this inverse Laplace transform of e to the negative s times all this is f of t minus a, so t minus 1, then times the unit step function at t minus 1. Right, by the second translation theorem. And we have f here, and I'm just replacing t with t minus 1, and we get the following. So y of t, our solution to the initial value problem, is 5 times the quantity 1 minus e to the negative t minus 1, which would be 1 minus t power, times the unit step function at t minus 1. And there you go. All right. This is a perfectly valid way of writing the solution to our initial value problem. Now you could also write this as a piecewise defined function, right? Remember, you should be able to go back and forth between using the unit step functions and piecewise defined functions. Say y of t equals, now remember, this unit step function, when t is less than 1, this will be 0. So nothing. It'll be 0 when t is between 0 and 1, like this. But then when t is 1 or greater, the value of the unit step function is 1, and so you're left with this, 5 times the quantity 1 minus e to the 1 minus t. This is when t is greater than or equal to 1. I mean, you could write it as a piecewise defined function as well, if you wished. Okay? But yeah, but this is totally valid, though, right, with the unit step function, or the Heaviside function written in. Again, please, if you're unfamiliar with what all just happened, look up my video or read in your books, whatever books you might have, about the second translation theorem or translation about the t-axis for Laplace transforms. Alright, so I got just one more example of something like this. Again, very similar setup. It's just another first degree equation. Obviously, you could do higher degree equations involving piecewise defined functions as well. But yeah, I'm only going to stick to doing some first order examples just to keep things simple. Alright, so here I have y prime plus 2y equals some function of t, where the initial condition is again y of 0 equals 0. And that's not always going to be the case, just so happened for these two examples I chose. And this function of t is, t when t is from 0 to 1, not including 1. And it's equal to 0 when t is greater than or equal to 1. Sorry, that should be greater than or equal to 1. Right. Okay, so again, you could do two different setups and make a piecewise defined function. Replace f of t with t and solve that non-homogeneous equation for y and say, oh, that's the solution, y equals this when t is between 0 and 1 here. And replace f of t with 0 and solve that homogeneous equation and say, oh, y is this function when t is greater than or equal to 1. But rather than do all that, though, I'm going to rewrite this function involving the unit step function. So again, first piece, t. And then I'm going to take that piece away after 1. So t minus t times the unit step function at t minus 1. And then I add on 0 times the unit step function at t minus 1, but that's not good. All right, there's no reason to add 0. So there we go. Here's a way to rewrite f of t without pieces. Right? These are the same function. They mean the same thing. So now I have the following: y prime plus 2y equals f of t is this t minus t times the unit step function at t minus 1. Alright, then the first step in all this is, take the Laplace transform of both sides. So I got the Laplace transform of y prime plus 2 times the Laplace transform of y equals, now I'll break this up here into the Laplace transform of just t minus the Laplace transform of t times the unit step function at t minus 1. Okay. So again, the Laplace transform of y prime would be s times capital Y of s. That's the Laplace transform of y, right? Capital Y of s. Plus 2 times the Laplace transform of y is again the capital Y of s. Oops, sorry. I automatically took away the 0. Sorry, this would be minus y of 0, wouldn't it? Right. But I just already got rid of it because y of 0 is 0. My apologies. It should be s times y of s minus y of 0. And then plus 2y of s equals, now the Laplace transform of t would be 1 over 2, it's 1 factorial over s to the 1 plus 1, so that's 1 over s squared. And then again, different color. Using the second translation theorem. Which again, if you don't recall, please look at my last video. The second translation theorem, this will be, the value of a here is also 1. This would be minus, and then, e to the negative 1s times the Laplace transform of t plus 1. All right. So the Laplace transform of t plus 1 is 1 over s squared plus 1 over s. Right. So again, I leave it to you to figure out where that all came from. All right. If you don't recall from, go look at my last video on the second. I know I've been saying that a bunch, but okay. So now let's do some things here. Now this is 0, right? Y of 0 is 0. Then we solve for y of s, right? So second part, solve for y of s. All right, so y of s, now if I pull y of s out, that'd be s plus 2. So this will be 1 over s squared times s plus 2. Just dividing through by s plus 2. And then minus e to the negative s times 1 over s squared times s plus 2. And then minus e to the negative s again times 1 over s times s plus 2. Okay. Now I'm almost there. All right, the only thing I need to do now is, this might take a little bit, take the inverse Laplace transform of both sides. So I'll do this on the next page. This is the end, right? But before I get to that, what I'm going to do next is I am going to take 1 over s squared. So we'll do some partial fraction decomposition first. All right, PFD. I'm going to take 1 over s squared times s plus 2 and find its partial fraction decomposition. So that'll be some constant over s plus some constant b over s squared plus some constant c over s plus 2. Multiplying through by the denominators. 1 equals a times s plus 2 plus b times s plus 2 plus c times s squared. All right. Multiplying some stuff out, we'd have as squared here plus 2as. We have bs, right, plus bs plus 2b plus cs squared, and this is equal to 1. So a plus c, the coefficients of s squared, needs to be 0. 2a plus b, right, the coefficients of s need to be 0 as well. And the constant term 2b needs to be 1, the constant term over there. So from all this, we can see that b would have to be a half. All right, and if b were a half, a would be negative 1/4. And if a were negative 1/4, c would be positive 1/4. All right, so this 1 over s squared times s plus 2 is negative 1/4 over s plus 1/2 over s squared plus 1/4 over s squared, s plus 2. All right. Great, so let's keep that in mind. I'll put a little highlighter around it. This isn't the answer or anything, just keeping that in mind, keeping it highlighted. All right, and then I'll do the same for the other fraction I'm seeing, 1 over s times s plus 2, and this should be take a little less time. 1 over s times s plus 2, again, is some constant over s plus some constant over s plus 2. So 1 would be a times s plus 2 plus b times s. If s were 0, you'd see that a would have to be a half. And if s were negative 2, b would be negative half. Right? So putting those in, this would be a half over s plus negative half over s plus 2. Okay. All right, so now that I've got these, and I'll put that in a bubble as well. All right, now that I've got these, let's go through and do the inverse Laplace transform of all this. And these expressions involving e to the negative s, I'm going to be also needing to use the second translation theorem to state their inverse Laplace transforms. All right, so third part, inverse. So y of t equals, the inverse Laplace transform of 1 over s squared times s plus 2. Now we can see from here, 1 over s squared times s plus 2 is negative 1/4 times 1 over s. Well, the inverse Laplace transform of 1 over s was 1, so it's negative 1/4. Right? 1 over s squared, that was t. So the inverse Laplace transform of 1 over s squared was t, so plus 1/2 t. And then 1/4, now 1 over s plus 2 has an inverse Laplace transform of e to the negative 2t. So plus 1/4 e to the negative 2t. All right, so that's from this first fraction. All right, that's from this first fraction, these three terms. All right. Then, the next part, I have minus e to the negative s times all this. And really, it's just going to be it's the same fraction. Right? It's 1 over s squared times s plus 2. The only difference is multiplied by this e to the negative s. Well, if that's e to the minus 1s, so I take this here, this, and put in t minus 1, and we get that times the unit step function at t minus 1. So this is what I mean. This is what I mean. So the second part is minus, right, minus, and then this e to the negative s, 1 over s squared times s plus 2, the Laplace transform of this would be the following. It would be this function, but with t minus 1 instead of t. So let me show you. Negative 1/4 plus 1/2 times the quantity t minus 1 plus 1/4 times e to the negative 2 times the quantity t minus 1. All right, all that times the unit, this is going to be gross, times the unit step function at t minus 1. That's the, sorry about that, that's the unit step function at t minus 1. All right. And then the last part also has this minus e to the negative s. So again, I'm going to be using the second translation theorem. Now, if I were doing the inverse, if I said what's f of s here, if I said what's f of t, little f of t, what's the inverse Laplace transform of this expression, the 1 over s times s plus 2? Well, we did the breakdown. This would just be a half minus a half e to the negative 2t. All right. But again, I've got this e to the negative s in front of it, so this is t is going to be replaced with t minus 1. I take this function at t minus 1 times the unit step function at t minus 1 as well. All right, so this is going to be minus again, because you got minus, and then this inverse Laplace transform of e to the negative s times 1 over s times s plus 2 would be this function at t minus 1, so 1 half minus a half times e to the negative 2 times t minus 1 times the unit step function at t minus 1. All right. And then, if you wished, we can simplify stuff, because notice how both these here have the unit step function at t minus 1 in common. All right. So I am going to simplify this in a second. Okay, so it's just a bunch of algebra now. All right, the rest of this whole thing is pretty much set and done after application of the second translation theorem. All right, so let's do this. So I've got the negative 1/4, got the plus half t, and plus a fourth e to the negative 2t. All right, and then what I've got is minus, both of these have like minus the unit step function at t minus 1 in common. And then we'll do some distributing and whatnot. When I pull out the minus unit step function at t minus 1, I'm left with negative 1/4 plus a half t minus a half and plus a fourth e to the 2 minus t. Yeah, let's just make that 2 minus 2t. So plus a fourth e to the 2 minus 2t power. And then again, I pull out minus this, so it'd be plus, this is all in the brackets, plus a half minus half of e to the 2 minus 2t. And then in the brackets, I can combine some like terms. And when all is said and done, we have the following. Y of t equals negative 1/4 plus 1/2 t plus 1/4 e to the negative 2t. And then I'll just put the minus here, and I'll put, usually the unit step function goes at the end. Minus, and then in brackets, let's see, combining some like terms here, we have negative 1/4 minus 2/4 would be negative 3/4 plus 2/4 would be negative 1/4. All right. So yeah, it's negative 3/4 plus 2/4, so negative 1/4. Then there's only the half t there. That's the only t term, so plus half t. And then I've got both of these, e to the 2 minus 2t power terms. You got that's a fourth minus a half, 1/4 minus 2/4, that's negative 1/4 minus, so minus 1/4 e to the 2 minus 2t power. But this thing in brackets is multiplied by the unit step function at t minus 1. And yeah, that's a pain there. Wow. Still doable though, still manageable. I managed it. Right. There is the there's your result. Okay. There's your result. And you could again break this up and write this as a piecewise defined function if you wish. You know, y of t equals something from t equals 0 to t is less, between 0 and 1, and y equals something else when t is greater than or equal to 1. Right. And I'm not going to get into that here because that would involve some more addition. Because when t is less than 1, the unit step function would be 0. So this is what you'd get when t, this function is the solution when t is less than 1. But when t is greater than or equal to 1, right, the value of the unit step function is 1, and then you'd have to add these, just combine some like terms, and actually I think negative 1/4 minus negative 1/4 would be gone, half t minus half t would be gone, and actually that wouldn't be so bad. But you could get another you could break this up and write it as a piecewise defined function. Okay, so yeah, a lot of stuff there, a lot of stuff going on. The hardest part I feel is remembering the second translation theorem, which I've been saying out loud. And again, hopefully you know what it is, you've read it, you've seen my other video using it, and I'm just using it here in application of, while solving these initial value problems. All right, and hopefully watching me do these couple examples help you out when you're working on problems like this on your own. And thank you very much for watching.